Hello and welcome. In this worked example, we're taking a look at question number 7, which relates to both the chapter on radioactivity, but also chapter 7, electric fields. And the question reads, state a similarity and the difference between an up quark and an up antiquark. So the obvious difference there with this word anti is, like one's an antimatter, the other one is regular matter. So up quark is made of matter, and the up antiquark, as the anti suggests, is antimatter. The other key difference that every student of physics should appreciate between matter and antimatter is that antimatter has the opposite charge of matter. And so we know that an up quark has a charge of positive 2/3, and an up antiquark, which we use the bar, so U bar is the up antiquark, has a charge of negative 2/3. And so they have opposite charge. A similarity with matter and antimatter is that they have the same mass. And so that's really a key idea here. You wouldn't want to let this kind of a notation stand as your answer on paper 2. Okay, even though the examiners that are grading this know that this symbol means, up and this means anti-up, you would want to sort of, they give you all this space here to state that in words. And so you'd want to sort of write it that way. An up quark has a charge of positive 2/3. The up antiquark has a charge of negative 2/3. That's a difference. Don't just let this sort of symbolic notation stand as your answer. We see that in part B here, it reads, figure 7.1 shows an electron in an electric field in a vacuum at an instant when the electron is stationary. On figure 7.1, draw an arrow to show the direction of the electric force acting on the stationary electron. Because they're showing us that the electric field is sort of pointing in this direction, the electric field lines are sort of more concentrated on the right side and less concentrated on the left, but they're all pointing, to the left. That's the direction that a positive charge would move, right? So the rule here is that the direction of an electric field is the direction that a positive charge would move. An electron, being a negatively charged particle, is going to then experience a force in the opposite direction of the electric field, so to the right in this case. It says in part 2 that the electric field causes the electron to move from its initial position. And the next question says, describe and explain the acceleration of the electron due to the field as the electron moves through the field. Describe and explain the acceleration of the electron due to the field as the electron moves through the field. All right, so an electric field is the force per charge. And so as it's experiencing a force to the right, it's going to accelerate. And if it were a uniform electric field, it would just have constant acceleration. But because the field is getting stronger, as it moves to the right, it's going to feel a greater force and therefore accelerate more. All right, so the two equations that we can kind of use to sort of anchor our thoughts here are the equation for the electric field and Newton's second law. So a stronger electric field is going to mean stronger force, and a stronger force is going to mean greater acceleration. And you kind of want to put that in your own words right here, right? Describe and explain the acceleration. So the acceleration is going to increase. That's a description. The explanation is that because there's a stronger electric force, because it's moving into a stronger electric field. The electric field is stronger at the right. And we know that because the greater density of the electric field lines indicates a stronger electric field, right? Those lines are closer together on this side than they were on the left. And so the electric field is stronger there. All right, and then the final part of this question says a stationary alpha particle is now placed in the same electric field at the same initial position that was occupied by the electron. Compare the initial electric force acting on the alpha particle with the initial electric force that acted on the electron. All right, so you may want to consider What is the source of this electric force? Of course, don't worry, we'll edit it in later, you guys. So the electric field is the force per charge, and we're comparing the initial electric force on the alpha particle. So like what's different between an alpha particle and an electron? We were mentioning earlier that the alpha particle has a charge. We use letter Q for that. So the charge of an alpha particle is positive 2 elementary charges because there's 2 protons. Remember, an alpha particle is a helium nucleus, and helium is something with 2 protons. The charge on our electron is -1 elementary charge. Because the alpha particle has twice the charge, it's going to experience twice the force and in the opposite direction of the electron, right? Because it's positively charged, it's going to be pushed in the direction of the electric field, which you remember was pushing it, to the left, where the electron drew the force pushing it to the right. So those 2 key differences you'd use to compare. The force acts in the opposite direction and with twice the strength or twice the magnitude. This is Dr. Schleif, still living the physics life. We'll see you next time.